In our second lesson this unit, we're going to focus on applying the Pythagorean theorem, its converse, and working with those to find the area of triangles that are not necessarily right triangles, or maybe they are. However, we will be applying the Pythagorean theorem and using it to find the area of triangles. Our job is to use the Pythagorean theorem and apply that converse of the Pythagorean theorem. That might be new material for you. You might not have too much, in your background dealing with the converse of the Pythagorean theorem. However, we're going to do our best to figure that out, learn that today. So there's going to be a lot of text for our theorems today and our converses and corollaries, but the goal here is not to necessarily have all of the text. There's all the text, etc. But what I care about here is the picture and the equation. You're all familiar with this notion that in a right triangle, the sum of the squares of the lengths of the legs is equal to the square of the length of the hypotenuse. All right, so you're familiar with that concept of a squared and b squared add up to c squared. And you've done a number of exercises and practice in your Algebra 1 and pre-algebra classes, maybe even in some elementary arithmetic classes, depending on your situation or your exposure to that. But we are going to use that to find the lengths of sides in our triangle. And so along the way, we may get to or may have to use simplest radical form. All right, so where appropriate, we're going to use our simplest radical form. But for each one of these, we want to make sure that we have and establish quality habits of our work. So for this first one, we're going to say that a squared and b squared equals c squared. We're going to write our formula for each one of these items to find x, to find y, and to find z. In this case, these are going to be the legs, so this can be a, and this can be b, and then this can be side c. So we'll have 20 squared and 21 squared is equal to x squared. We get to do our calculations, wherein we square each of these numbers. And then that will let us determine the value of these variables, all right? Now we are going to do our basic addition. And then we get to this situation, and at the end of our last in-class practice with in working with the area of triangles, we had some exercises where we had variables that were squared, and that kind of forced us to handle how do we solve those types of equations. And the answer there is we want to take our square root on both sides. And so when we square when we square root both sides, we find out that x is equal to 29. Maybe it's helpful if I write this as a step. Whoops. And then we can take our square root on both sides to find out that x is equal to 29. So here we took a Pythagorean theorem question, and obviously we have the formula, we plug in the variables, we compute our operations, we combine our like terms, we take our square root. So there's maybe a step in here that we could skip, but overall it's going to take us 4 or 5 lines of work. Now for y, we're going to do the same thing. A squared and b squared equals c squared. Here's a situation where we know what a is, what b is, and c, but a is our variable, right? We've got y squared plus 12 squared equals 16 squared. We get to use our times tables or our calculators to find out what these items are when we square those. And then we get to use our calculators to do some subtraction so that we can find out what y squared is equal to. All right? Now we're going to have a situation where simplifying this radical is going to force us to use simplest radical form. We find out that 112 is the square root of 16 and the square root of 7. Or I'm sorry, the square root of 112 is the square root of 16 and the square root of 7. Which means that y is equal to 4 times the square root of 7. If there are units, we write the units at the end. Once we know what our side length is, we apply the side length with the units and move from there. Go ahead and try letter Z. We're going to have a squared and b squared equals c squared. In this case, we will have A, B, and C. It doesn't matter which ones are A and B. It just matters that you're able to identify the legs and the hypotenuse. All right, the hypotenuse needs to be its own thing. And so we've got 64 and z squared add up to 400, and so z squared is equal to 336. This is going to be divisible by 16 again. And we're able to write our answer in its simplest radical form, 4 times the square root of 21. So when we are working the Pythagorean theorem here in the high school math, we are going to sometimes have situations that work out nicely where we have integer answers or whole number answers. That is awesome in geometry class. At times, however, we have a radical that will need simplified, and we'll need to make sure that we practice that as we have in recent exercises. All right, a Pythagorean triple. This is something that I want to include in your notes, but it is only as valuable as you are, or as you're able to remember these Pythagorean triples. Basically, Pythagorean triples are sets of whole numbers, a, b, and c, that make a squared plus b squared equals c squared. So here are a couple Pythagorean triples. 3, 4, and 5, 8, 15, and 17 are a Pythagorean triple. And what we want to understand with this is if we apply these Pythagorean triples, a 3, 4, 5 triangle would be a right triangle, right? 3 squared plus 4 squared makes 5 squared. But if we understand that this is true, then it also applies to the multiples of these numbers. If we multiply each of them by 2, 6 squared and 8 squared are going to add up to 10 squared. If we multiply each of these by 3, then 9 squared and 12 squared will add up to 15 squared. All right, and so we can trust that if this works at its basic level, that all of the multiples will satisfy a squared plus b squared equals c squared. With 8, 15, and 17, we have 64 plus 225 equals 289. 8 squared plus 15 squared is equal to 17 squared. But if we trust that, or if this is true, then we know that multiplying each of these numbers by 2, or tripling each of these numbers, multiplying them by 3, is going to give us another set of A, B, and C whose squares satisfy the Pythagorean theorem. All right, 24 squared plus 45 squared equals 51 squared. You can even check that in your calculator if you'd like. All right, those are Pythagorean triples, and there are plenty of others. You'll notice that there's a little gap in there. We're going to chat about that here in just a bit. But the goal there is to show that we have, if we know these Pythagorean triples, it saves us the hassle and the time that it would take to actually solve an equation using, 2 of these to find the 1, or using 2 of these to find the 1, or in the multiples here, saying, all right, I have 9 for a leg length, I've got 15 for a hypotenuse, what is the other leg's length? If I know my Pythagorean triples, then I can answer that question much more quickly without having to do the whole process of the Pythagorean theorem. So basically, are these sets of numbers a Pythagorean triple? Basically, the largest number is always going to be your C value. So I usually go A, B, and C. A, and B, and C. And basically, the question here is, if we're finding out are these a Pythagorean triple, then we're asking ourselves, does A squared and B squared equal C squared? What is that relationship? What does that look like? So if I take 5 squared and I add 12 squared, what is my relationship to 13 squared? All right? What is that relationship going to be? Are they equal to each other? Is one bigger? Is one smaller? And so we want to find out what happens when I take 25 and 144. How does that relate to 169? Well, it turns out that those are indeed equal. So yes, 5, 12, and 13 is a Pythagorean triple. Okay? With 6, 8, and 9, if you already know that 6, 8, and 10 is a multiple of the 3, 4, 5 set, then we know that this is not going to be a Pythagorean triple. Still, we're going to check it. We're going to write our formula down, and we're going to ask the question, how are those related to one another? Are they equal? Is one greater? Is one smaller? And let's do 6 squared and 8 squared and compare it to 9 squared. If I take 36 and 64, that will not equal 81. 100 does not equal 81. And so therefore, 6, 8, and 10, and 9 are not a Pythagorean triple. Okay? If it works out, great. If it doesn't work out, also great. It's just a matter of recognizing it or discerning it through computation. Okay? This is the punchline. This is what we actually want to do with this. So of all the work that we've done so far, this is going to be the most applicable to our task today. The goal here is to be able to apply the Pythagorean theorem so that we can compute the area of these triangles. And as you note, we have here an isosceles triangle, and then we have this altitude drawn here. Over here we have a right triangle. I have a length of one of the legs, but not the other leg. And so the question is, how do I find out what this is so that I can know what the area is? How can I find out what the height of this isosceles triangle is so I know what the area of the total triangle is? And that's going to require that we do a little bit of computation. Over here, if I want to find out this h value, then where I want to put my attention and energy is into recognizing my situation. In an isosceles triangle, the altitude is the perpendicular bisector of the base. All right? We know that from Unit 4 last semester, which means that I can call this 10 and this 10 and this is 12. I essentially have this basic triangle over here with 10, h, and 12, and my job is going to be figuring out what is the height. But again, I'm not finding the area of this triangle, I'm finding the area of this whole set right here. So be aware that our work is not going to be done once we find out what the height is. So I write down my formula, just like always. A squared and b squared make c squared. In this case, 12 squared and h squared equal 12 squared, because 12 is the hypotenuse, so that has to be on its own side of the equal sign. We've got 100, we've got h squared, we've got 144, which means that h squared is equal to 44 when I subtract 100 from both sides. And so that means that h is the square root of 44, and now we have work to do. Generally speaking, I would expect 1, 2, 3, 4, 5 steps, but here we have additional work to do. Taking the square root of 44 is the square root of 4 and the square root of 11, so the height in this case is 2 times the square root of 11. That's not the answer to the question. The answer to the question is, what's the area of this figure? Well, I have the base of 20. I now know the height is 2 times the square root of 11. So now I can find that the area of this triangle is 1/2 times the base times the height, just like we did on our lesson 1 from this unit. Tell us that the base is 20, the height is 2 times the square root of 11. And a little pro tip for you. If you have to do this calculation, multiply everything that's not in the radical in your calculator, all right? And then multiply that by the square root of 11, and that will be your answer, all right? So it makes this work a whole lot easier if you end up with 20 times the square root of 11 square units, all right? Because the height is actually in meters as well. So make sure that we have our units applying. Go ahead and try the second example here, or the second item on this example 3. You can pause the video. But again, here's how that work goes, all right? So if you already did it, awesome. Let's check our answers. We have a squared plus, there's my height, b squared is equal to the square root of 53 squared. This is a little awkward, but hey, guys and gals, fun fact here. If I square the square root of 53, I just get 53. Try it in your calculators if you don't believe me. When you subtract 49 from both sides, you find out that b squared is equal to 4. So b is equal to 2, in this case, centimeters. We know that. We're going to apply that as the height of this triangle. So area is equal to 1/2 base times height. I hope that that example went well for you. If there was something that you did differently than I did, go ahead and check that to make sure that you feel good and groovy about how you did with that. Make any corrections that you need to make. All right. Here again is a massive amount of word vomit on the screen here. You do not need to copy that text verbatim. I do encourage you to read it, but basically these are the converses for the Pythagorean theorem, well, the converse and then some extensions that follow suit. The first is, if c squared is equal to a squared plus b squared, then we know that our triangle is the right triangle. Now what that means, like, well, how do you know which one's C and A and B? Well, C is going to be the longest side of your triangle. That's true in a right triangle, that C is the hypotenuse. So if you square the longest side, and then you add the squares of the two other sides, if that makes a true equation that the length of the longest side squared is equal to the sum of the lengths of the other two sides, then this is a right triangle. All right, so think about the Pythagorean theorem. Think about how we write converses, how we flip those statements around, the ifs and the thens. And then this should be true for you. If we can find out that a squared plus b squared actually equals c squared, then we know that our triangle is a right triangle, because this is only true in a right triangle. So you just need this and you just need that. Do not have all that text. It's not necessary. Now, there are converses of that as well. You'll notice that this converse, that there are some corollaries to that. So I want to follow that in just a moment. But here, notice how they flipped the equation. They said if this is equal to that, not if that is equal to this. All right, so the equation is written using the symmetric property of equality. It's written in reverse, if you want to think about it that way, where if c squared is equal to a squared plus b squared, then the triangle is right. And then we have these follow-ups. If c squared is greater than a squared plus b squared, then that triangle is obtuse, because c squared is greater than, obtuse is greater than 90. And then there is, again, this theorem 7.7. If c squared is less than a squared and b squared, then the triangle is acute. Now here's where students mix this up. We put this first, and then we put greater than c squared for acute. And that is backwards, right? It's factually true, but then it messes with our line of thinking. So we want to flip this c squared less than a squared plus b squared, c squared greater than a squared plus b squared, and c squared equal a squared plus b squared. Right triangle, obtuse triangle, acute triangle. And so obviously we're going to have questions just like the Pythagorean triple. Does this, is this a Pythagorean triple? Yes or no? That was the question, how it was framed in that previous example. Here the examples are going to be framed saying, are these right triangles? Are these right triangles? Are they acute triangles? Are they obtuse triangles? So when you have each of those pictures, then, once you have all those pictures, then we can actually ask the question, is c squared related to a squared and b squared as equal, as greater than, or as less than? So we're going to take 85 squared, we're going to have 84 squared and 13 squared, and we're going to try to find out what the relationship is between this sum and that product. It's going to require that we use our calculators. I'm not expecting you to do this without a calculator. I've got 7225 over here. I've got 7056 and 169. And when I add those up, it turns out that these are equal to each other. So yes, this is or not yes, it's not a yes or no question. This is a right triangle. Because it satisfies the Pythagorean theorem. On the other end, we want to say this one's not going to work out. We know that that's not going to work out, but we can at least pretend that we're engaged with that. So what is the relationship between c squared and then a squared plus b squared? So 7 squared as it pertains to, or as it compares to 4 squared and 6 squared, we have 49, we've got 16, we've got 36. When I add these up, I find out that 49 is less than 52. Therefore, this is acute, or an acute triangle, all right? Because c squared is less than a squared plus b squared. All right, over here, 11, 12, and 15. We're gonna compare c squared to a squared and b squared. You can pause the video and do that on your own if you'd like. Here we find out that when we do that summation, we end up with a total that is bigger than the sum of, a sum that is bigger than the length of the longest side squared, and therefore we will say that this is acute. All right. Obviously, if c squared were greater than a squared and b squared, we would end up with an obtuse triangle. Okay. Folks, that is kind of the end of the information and the examples from this lesson. The key here is that we make sure that we apply the Pythagorean theorem to find area, that we understand Pythagorean triples, that we understand the converse of the Pythagorean theorem, but that we are able to use the Pythagorean theorem in computing the area in triangles where it is not very apparent how to approach it. So for our last example, example 5, this is the tough part. We've got all the information. That is it for the information. But now we're going to look at how to apply this. So the area is known. Here the area of this triangle is 20 square feet. Find the length of segment AC, find the length of segment BC, but write your answer in simplest radical form if needed. So I do not know what the length of AC is, that's why we have to find it. I do not know the length of BC, that's why we have to find it. And so the question that we want to ask ourselves is, how do we find out what the lengths of these segments are? Well, folks, here is the good news. The good news is we already know the area of this triangle is equal to 1/2 times base times height, all right, per our previous lesson. We know the base is a total of 10 feet. The height we're going to find just like we did in lesson 1 a few times. And so we're going to take that the area is equal to 1/2 of the base times the height, so that we can find out the length of this segment. Let's call it, we can call it CD if we want to. It doesn't actually matter, but maybe you write that in your picture. That way I'll know that you took the notes. Write CD, call this point D in your picture. That way I'll know that you did your notes. So 20 is equal to 5 times h, which means that 4 feet is equal to the height. All right, so now we know that this is 4 feet long. And we can use a squared plus b squared makes c squared, and a squared plus b squared makes c squared, so that we can know the lengths of these segments. All right, so let's go ahead and do that. A squared and b squared make c squared. We're going to have 2 feet and 4 feet make the length of segment AC squared, right? We're trying to find the length of segment AC. So I get 4 and 16 is the length of segment AC squared, which means 20 is the length of segment AC squared, and now I have to take the square root of 20 to get the length of segment AC. When I take that square root, we've done that enough where we have the square root of 4 and the square root of 5 is the length of segment AC, which is 2 times the square root of 5 feet. Answer with units. On the other side over here, we're going to have the same a squared and b squared makes c squared, but we have 4 and 8 make the length of segment BC squared. So now 16 and 64 make the length of segment BC squared. This is 80 is the length of segment BC squared. We've had the square root of 80 a few times in our work back in January. And so the square root of 80 is going to be the square root of 16 and the square root of 5, which means that we have 4 times the square root of 5 is the length of segment BC. Feet. So we found those. Now, fun fact, if you want a bonus point on your notes, go ahead and do area equals 1/2 base times height, and show me mathematically that you can get the answer for the area of that triangle using these sides as your base and your height. All right, that is the end of that lesson. That one was a little bit longer than the last couple. It's 20 minutes, 24 minutes. So make sure that you are able to apply that Pythagorean theorem so that you can find area as needed. See me with questions.